Okay, people, on to example 3. Take a little break there for a second. Or at least I hope it's example 3. I mean, ain't that gonna happen? Maybe I might drop one. Probably not though. I'm like, oh, only if I find a mistake, which gosh, I hope not. But anyway, the point is, yes, let's do another example of this one-to-one onto all that jank. Don't be blurry. Don't be blurry. They'll go away. So this example is an interesting one. Probably the most interesting one we've done so far. Wait, let's use the whole whiteboard here. There we go. In this example, we want to let h be some function that goes from the natural numbers union 0, so all integers greater than or equal to 0, to the full set of the integers. And that's not going away, so I'm going to stop my share, then start it again. And it's like nothing happened. Nice. So we have, this is the domain of the codomain of our function. What is our actual function? So we're going to define our function to be h by h of n is going to equal, and it's going to be a piecewise function. And here's where things get interesting. So remember, a piecewise function, what h does to n depends on what n is. And so we're going to have 3 cases. We're going to have if 3 divides n, if 3 divides n minus 1, and otherwise. And notice these 2 cases are distinct because if 3 divides n, it will not divide n minus 1, by the fact we proved like the next lowest multiple will be n minus 3 or n plus 3, right? So because n and n minus 1 are just 1 apart, if 3 divides n, 3 won't divide n minus 1. So these are 2 different, like these won't ever overlap. If 3 divides n, we want h of n to do, we want to output negative n over 3. If 3 divides n minus 1, we want h of n to output n minus 1 over 3. And then we want to output n otherwise. Okay, that makes sense to me. These are the piecewise things that our function does. So let's just do an example here. If we take like h of negative 5, for example. Well, let's see here. Notice that negative 5 minus 1, 3 does divide that. 3 divides negative 6. And so this is going to be negative 5. Oh, wait, I'm sorry. Wait. We can't even have negative 5 because we have natural numbers union 0 is our domain. So let's do 5. So as for 5, 3 does not divide n minus 1 is 4, 3 doesn't divide that. So the output is just the input, just 5. H of 6, though, well, 3 does divide 6. So this is going to be, actually, you know what, let's just go in order. So we start with h is 0. For h0, we get, well, 3 does divide 0, technically, because 3 times 0 equals 0. It's an integer multiple of 0, or 0 is an integer multiple of 3. So 3 divides 0, so that means it's going to output negative 0 over 3, which equals 0. Now, h of 1 is an equal sign, by the way. H of 1, what's that going to equal? Well, here 3 does not divide n, 3 does not divide 1, but 3 does divide n minus 1. 3 divides 1 minus 1, which equals 0. So that means we're in this case. In this case, the function outputs the input 1 minus 1 over 3, which is again 0. Now, h of 2 is an interesting case. So h of 2, oh, actually, no, it's not that. I'm sorry, it's not that interesting. H of 2, 3 does not divide n, and 3 does not divide n minus 1. So we go to the otherwise case. 3 does not divide 2, 3 does not divide 2 minus 1, which is 1. So we go to the otherwise case. So we output just n, which is 2. H of 3, here 3 divides n again, so in the top part. So we output negative the top, negative 1. H of 4, notice that h of 4, 3 divides n minus 1, 3 divides 4 minus 1. So here we're going to output 4 minus 1 over 3, which is 1. And then h of 5 is again h5. 3 does not divide 5, 3 does not divide 5 minus 1. So in the otherwise case, we just output 5. Then we keep going. H of 6, 3 does divide 6. That means in this case, we're going to output -6 over 3, which is -2. H of 7, this is going to equal, if you plug 7 in to n here, or sorry, 3 does divide 7 minus 1. 3 divides 6. So that means we're in this case, so we get 7 minus 1 over 3, which is 2. Do you see the pattern here? What's happening is this case and this case keep generating all the positive and negatives of the integers in order. So you plug 0 in, you get 0, you get or -0 kind of, and 0. That's just 0. And then you skip over the otherwise case, and you get -1 and 1. You skip over the otherwise case, you get -2 and 2. And it's going to keep going like that. That's what happens here. The otherwise case is just kind of weird extra bits, which might not be good for a one-to-one or onto situation, or sorry, one-to-one situation, because immediately we have two outputs that go to, or two inputs that, or two distinct inputs that go to the same output. So that's no good. So immediately, actually, I'm going to point out, so we don't have to do it later. H naught one-to-one. But anyway, this is what the function does. Keep that in mind as we talk about it into the future. So, first of all, let's talk about well-defined. So this well-defined business. Remember, our function is well-defined if every input has exactly one output. And the only real case we could run into trouble here is with this overlap kind of business, right? Because if these two cases overlapped, well, then we would have two possible answers. Like if there was a number that was both divisible by 3 and n minus 1 was divisible by 3, if that number existed, well, then kind of both of these would be our output, and that's no good. We don't want that. So what we want to note that H is well defined is we want to say first, note that for each input in n union 0, 3 divided by n, and 3 divided by n minus 1, or I'll say, I'm sorry, for each input in here, negative n over 3 and n minus 1 over 3 give one output each. I'll say negative n over 3, n minus 1 over 3, and n give one output each. That's totally true. Why is that important? That's important because, you know, as long as these don't overlap, that means we're going to have one output. This gives one output, this gives one output, this gives one output. And so as long as these cases do not overlap, our function will consistently just give us one output. So further, for all n in our domain here, natural numbers union 0, 3 divides n we can't have 3 divides n and 3 divides n minus 1 simultaneously. If we did, then 3 would divide n minus n minus 1, which equals n minus n plus 1, which equals 1. And 3 does not divide 1. So there's like a little contradiction there. If 3 divided n and n minus 1 simultaneously, we'd find 3 divides 1, which is not the case. Hence, for each n in the domain, we either have 3 divides n or 3 divides n minus 1, or neither, but never more than one case. Thus, there is exactly, thus H gives exactly one output for each input of, for each input, yeah. So, therefore, H is well defined. So all we're saying here is that if you give me any integer n, it's gonna be one of these two, exactly one of these cases. Whichever case you go in, this will give me exactly one output. That's it. That means it's one. That means well defined. I wish I just said that. I.e. for each n in the domain, n will satisfy one case, and each case gives one output. So H has one output. Really wish I just said that, honestly, but this is the long-winded reason of why all that's true. But this is the right to takeaway. Okay. Now, let's talk one-to-one, which we already talked about. One-to-one, claim H is not one-to-one. Proof that H is not injective, for the word for one-to-one. So remember, to prove something is injective, right, we have to show that if there are any two things in the input that map to the same thing in the output, or is there any two things in the domain that map to the same thing in the codomain, the two things in the domain must have been the same. If f of A equals f of B, A must equal. But to disprove that, to prove the bijection, to prove the negation, to prove that H is not injective, all we have to do is show that there exists two inputs in the domain that map to the same output in the codomain. And we already saw what those were. Consider A equals, what do we have? That's a good example. Consider A equals, I believe it was 7, yes. And B equals 2. Note, since 3 divides 6, which equals 7 minus 1, H of 7 would be, in this case, would equal 7 minus 1 over 3, which equals 6 over 3, which equals 2. Further, since 3 does not divide 2, and 3 does not divide 1, which equals 2 minus 1, we're not in this case, we're in the otherwise case. H of 2 equals 2. Therefore, there exists distinct inputs, 7 and 2, that map to the same output under H, that being 2. Thus, H is not one-to-one. So we circled them before, and now this is the formal proof that H is not one-to-one. So to prove one-to-one, assume that f of A equals f of B and show A must equal B. To disprove, just find A and B. that are different from each other, such that f of a equals f of b, or such that h of a equals h of b. You know what I mean? That map to the same thing. All right. Now, last we have onto. That's really the interesting one here. So onto is the interesting one. All right. So to prove a function, so first of all, do we think this function's onto? I'm going to say yes. Because of that kind of table thing we made in the very beginning here, we showed that we had h of 0 goes to 0, h of 1 goes to 1, h of 4 goes to negative, or sorry, h of 0 goes to 0, h of 1 goes to 0, h of 3 goes to negative 1, h of 4 goes to 1, h of 6 goes to negative 2, h of 7 goes to 2, h of 9 goes to negative 3, h of 10 goes to 3, on and on like that. We're actually going to ping pong around, it seems, and hit every single integer in the codomain. How do we prove it? And here's how we prove it. I'll say at the beginning, note from our observations, it seems that well, it's not only from observations, it's just from this. From this and our observations, we totally gather that in the case that plugging in the multiples of 3 will get us negative 1, negative, or sorry, will get us 0, negative 1, negative 2, negative 3, etc. And plugging in numbers 1 more than a multiple of 3 gets the positives. 0, 1, 2, 3. Not that 0 is positive, you know what I mean, etc. On and on and on like that. That seems to be what's happening here, right? And we can see that, right? If we plug in h of 0, we get 0 divided by 3, which is 0. H of 3 at 3 divided 3, we get negative 3 over 3, which gives us negative 1. Plugging in 6, the next multiple of 3, we get negative 6 over 3, which gives us negative 2. Plugging in 9, the next multiple of 3, we get negative 9 over 3, which gets us negative 3. This goes on and on like that. Now, if we plug in the, we consistently plug in the numbers 1 more than a multiple of 3, h of 1, now we're in this case. Every number 1 more than a multiple of 3 can subtract 1 so by 3, so we're in this case. So h of 1, for example, 1 minus 1 is 0, 3 divides 0, so we're in this case, so we get 1 minus 1 over 3, which is 0. H of 4 gets us 4 minus 1 over 3, we're still in this case, which is 3 over 3, which equals 1. H of 7 gets us 7 minus 1 over 3, which is 6 over 3, which is 2. H of 10 equals 10 minus 1 over 3, which is 9 over 3, which equals 3. So you see these numbers goes by 3, the multiples of 3 are producing the negatives, and these numbers 1 more than multiple of 3 are producing the positives. So here's how my onto proof is going to go. Proof that H is onto. So the proof goes like this. Again, remember, want to show for all M in our codomain Z, there exists an end, the natural number union 0, such that H of n equals n. That's what we're trying to prove. So let M be any arbitrary / particular element of Z. Note M is either greater than or equal to 0, or sorry, M is either less than or equal to 0 or M is greater than 0. So you have two cases here. Case 1, M is less than or equal to 0. Now, since less than or equal to 0, I want to generate it with these multiples of 3. So I'm going to let n be the mth multiple of 3, and I think when I plug it in, I should recreate m, proving we can hit m. So let's go ahead and let n equal 3 times the absolute value of n. Absolute value because m is negative, so I want the mth negative number, but m like the positive version of m. You see what I'm saying? Like if m was 2, I want n to be 3 times 2, which gets me 6. When I plug in 6, I get -2. Or sorry, if n was -2, I want n to be equal 3 times 2, which equals 6, which gets us -2. So I want to take like the positive version of this, that multiple of 3, that when you plug in should recreate your m. So let n equal m 3 times m. Then note, since m is absolute value of n is certainly in Z, 3 divides n. Thus, h of n, or in this case, where 3 divides n, will get us negative n over 3, which is -3 times absolute value of n over 3. These cancel out, and this gets you negative absolute value of n, which equals m. And this is true since m is negative. Right? If you take any negative number, like say -5, -5 is going to equal the negative of its positive version, right? Obviously. So this means that so for m less than or equal to 0, we could find an n. Oh, and we should note one last thing. Note, since absolute value of anything is greater than or equal to 0, 3 times n is in natural numbers. i.e., there exists an n, the natural numbers union 0, such that h of n equals m. So if n is less than or equal to 0, we can use like the multiples of 3 to get us exactly what we want. Now let's move down here. Let's get below the glare. All right. Now let's check out what happens if m is greater than 0. For numbers greater than 0, we really want to use the one more than a multiple of 3s. The 1s, 4s, 7s, 10s. Those would be 2. Recreate our m here. Specifically, it looks like h of 4 creates 1. Or 1's created by 4, 2's created by 7, 3's created by 10. So it looks like the number we actually want to use here is whatever this number is, multiplied by 3 plus 1. Looks like if you plug that into h, we'll get that number back. So if m is greater than 0, then let n equal 3m plus 1. Note 3m plus 1 is definitely in n union 0, the domain. Then, since 3 must divide 3m, which of course equals, since n divides, 3 divides n minus 1, which it does because this is going to equal 3m plus 1 minus 1, which equals 3m. Since 3 divides m minus 1, we have h of h of n is going to equal, where in this case now, it's going to equal n minus 1 over 3. n minus 1 over 3, which equals 3m plus 1 minus 1 over 3. Plus 1 minus 1 cancel out, so we get 3m over 3, which just equals m. Aha! So in either case, we can construct an n in the domain that we can specifically plug in to get n back. So in either case, there exists an n in the domain such that h of mn equals m. Therefore, h is onto. So the point is, this is complicated, but it's exactly the same as every other onto proof. All we have to do is go through and show that for any single m you pick in the codomain, I can find an n in the domain that when I plug into h will hit that m. And then we're done. So our h function here was complicated. It's a very interesting function. It was onto, but it was not one-to-one, but it was well defined. So that's why it's a function. But anyway, the really interesting thing about it was that h went from the natural numbers including 0 to z, which is odd because the natural numbers including 0 is a subset of z. In a certain sense, it feels like a smaller subset, right? Because it says this doesn't include any of the negative numbers. So it's weird that we were able to hit all of the z's, right? But actually not really. We kind of did a classic technique of kind of alternating where like one natural number went positive, one went negative, one went positive, one went negative, one went positive, one went negative. Kind of classic technique. But the point is, it shouldn't be that surprising because it's going to turn out that we can actually form a bijection between here and here. And once you can make a bijection between two things, that means they really kind of have the same size. So even though n and z feel like z is bigger than n, it really isn't. There's really, in a certain sense, the same number of elements. Really weird to think about, but interestingly true. So yeah, that's that example. Now, let me stretch. Now we're going to move on to doing some examples with bijections. Specifically, we want to show how you can prove that two sets have the same cardinality. So let's just go over the definition of cardinality again. Definition, two sets, I'll say sets A and B have the same cardinality if and only if there is a bijection from A to B. So this A and B are the same cardinality if and only if there is a bijection from A to B. And cardinality basically means size. If two sets have the same cardinality, it basically means they have the same size. That's literally true for finite sets. Note, if A and B are finite, as in they have a finite number of elements, and A has the same cardinality as B, A and B have the exact same number of elements. That's just a fact, but it gets much more interesting once you're dealing with infinite cases. So the first example I'm going to do is say prove prove that 0, 1, so the interval 0, 1 and the interval 5 to 100 have the same cardinality. And remember, since two systems have the same cardinality, if only if there's a bijection between them, really what we're asking is, to prove this, we need to find a bijection from 0, 1 to 5, 100, or other way around. Need to find a bijection between 0, 1 and 500. And what's a bijection? Remember, a bijection is a 1-to-1 and onto function. So it's a 1-to-1 and onto function, and so we have to check that's well defined to make sure it's a function 1-to-1. So let's get to thinking. So we want to find a function from 0, 1 to 5, 100. And here's the first thing we should notice. 5, 100 is a much, much, much bigger set than 0, 1. I mean, not bigger. We're going to prove this has the same cardinality, but it spans a greater area, maybe I should say, of the number line. And so what we really need to do here is we kind of really want to multiply by something to expand. That makes no sense. Let me explain. If we had, for example, f of x were to equal 100x, that was the function we're trying to make work as a bijection. If that was the case, notice that if we look at x here, and then we look at y, like the outputs, right? We have, we have x here, which is 0, goes from 0 to 1. Let's say this is 100, this is 0, this is 50, this is 75, this is 25. If you notice, if you talk about 100, 0 times 100 is 100. 0 times a quarter is 25, or sorry, a quarter times 100 is 25. A half times 100 is 50. 3/4 times 100 is 75. And then 1 times 100 is 100. So if you notice here, what's happening is, if you do f of x equals 100x, and then you plug in everything in 0, 1, it's gonna just spread everything out between 0 and 100. Because 0 times 100 is 0, 1 times 100 is 100, and we hit everything else in between. Hope that makes sense. So multiplying by 100 just kind of spreads everything out, really. But we really don't want, this interval doesn't cover 0. This interval doesn't cover like an area of 100 length. It covers an area of like 95 length, right? 5 to 100. So what we really want here is not f of x equal 100x, but f of x equals 95x. So then this will cover, once you plug in everything between 0 and 1, the range of this will range between 95 times 0, which is 0, and 95 times 1, which is 95. So this will range between 0 and 95. But that's not quite the same interval we have here. Like, this interval is 5 to 100, not 0 to 95. We want to shift our interval. If we add 5 to this, when you plug in 0, f of 0 is going to give you 95 times 0 plus 5, which is 5. When you plug in 1, you get 95 times 1 plus 5, which is 95 plus 5, which is 100. The plugging things in between will get us everything in between. So this is a very good candidate for our function. So let's let f of x equal 95x plus x. And now let's try to prove it's actually a bijection. So to be a bijection, we need to prove the following things. We need to prove theory of bijection. We need to prove that F is well-defined one-to-one. I don't want to. So let's do well-defined first. So is our function F here well-defined? Yeah. Function F is totally well-defined. Why is it totally well-defined? Well, because it's made up of 95 times x plus 5. And for each input, 95 times x is one output. And add 5 to that, it's still just one output. So note, for each input in the domain, oh, by the way, we should specify here that F goes from 0, that F goes from 0, 1 to 5, 100, just like we want, by fx is 95, x plus 5. Good. So for each input in the domain, which is 0, 1, 95x has one output, and thus the sum of 95x and 5 has one output. So F has exactly one output. So for each input, F has exactly one output. Therefore, F is well-defined. Now let's move on to one-to-one. So I'm going to say that F is one-to-one. And the reason being is because 95x plus 5, it doesn't seem like it would loop back around in itself. I think any two distinct inputs here will go to distinct outputs, especially because 95x plus 5, again, is increasing. So if you plug in two numbers, different numbers, well, one's going to be bigger than the other. So I expect 95x, I expect f of 1 to be bigger than f of the other, basically. So let's prove one-to-one. We're going to prove that. Goes like this. We always do the same thing. We assume there's two elements in the domain, just that f of a equals f of b, and then prove a must equal b. Assume there exists a, assume there exists a and b in the domain, which is 0, 1. Oh, such that f of a equals f of b. We want to show a equals b. Note, by definition of f equals 95x, f of x equals 95x plus 5. Since we have f of a equals f of b, we get 95a plus 5 equals 95b plus 5. Subtracting 5 from both sides, 95a equals 95b. Dividing 95 for both sides, a equals b as desired. Thus, f is one-to-one. So you've shown that if there are two inputs, that when you plug in, you get the same output. Those two inputs must be the same. There can't be two distinct different inputs that you plug in and get the same output. Therefore, f is one-to-one. So we're like two-thirds of the way there to being a bijection. The last thing we need to show is that f is onto. All right. And this is actually going to be maybe the easiest one of them all, because we did just some really simple algebra here. Because all I have to show is that if there's a y in 5, 100, we can find an x that we can plug in here to get to that. So we want x such that 95x plus 5 equals 100. Or sorry, no, equals y. We'll plug it in so it equals y. When x is 95x plus 5 equals y. But that implies that 95x equals y minus 5, which implies that x is going to equal y minus 5 over 95. It seems you plug in y minus 5 over 95 into f, you'll recreate y. So the only thing we have to show is that x is actually in a domain, which is going to be not that much. I'm going to erase the one-to-one part, though, to give me some more room. So proof, want to show for all y in the codomain, which is 5 to 100, there exists an x in the domain 0, 1, such that f of x equals y. To that end, let y be any arbitrary / particular element of 5, 100. And then like you can't see what I'm doing. Hold on here. Here we go. And then, like we showed in our little green aside, let x equal y minus 5 over 100. Is that what I want? No. Y minus 5 over 95. That's what we said in the thing before. There we go. Y minus 5 over 95. Note, since y is in 5 or 100, 5 is less than or equal to y, and y is equal to 100. Thus, if we subtract 5 from both sides here, 0, which equals 5 minus 5, is this equal to y minus 5. And y minus 5 is equal to 100 minus 5, which equals 95. Thus, 0 less than equal to y minus 5 less than equal to 95. Then, since 0 less than equal to y minus 5, we have that 0 over 95 just equals 0 is going to be less than or equal to y minus 5 over 95 by dividing both sides by 95. And since y is less than or equal to 95, y over 95 is going to be less than or equal to 95 over 95, which equals 1 by dividing both sides by 95 again. And since 95 is positive, you divide by a positive number, you don't have to change the signs or anything like that. Thus, 0 less than or equal to y minus 5 over 95 less than or equal to 1. So, y minus 5, so x, which equals y minus 5 over 95 truly is in 0, 1. So x really is an element of the domain. So x really is an element of the domain. Now to show is that this particular x you can plug into f to get y. If you can show that, that means that there does in fact exist an x you can plug into f to get y. What it shows it's onto 1-to-1, well-defined, meaning is a bijective function. So we have a cardinality. This is a line. Okay, let's go. Next, note that f of x will equal 95x plus 5 by definition, which will then equal 95 times y minus 5 over 95, because that's what x we said equals, plus 5 by substitution. And then the 95 is going to cancel out here, so we get y minus 5 plus 5 by simplification just equals y by more simplification. Thus, x is, so thus, for any y in 5 to 100, the codomain, there does exist an x in the domain such that y equals f of x. Hence, f is onto. Okay. That's our proof right there. So this shows that f is onto, because for any y you give me, any y you pick in the codomain, I can find x in the domain, mainly just by taking that y, subtracting 5 and dividing it by 95, that I know I can plug into f and get that y back out. So every single y is hit by a particular x. All right. So putting this all together, so all together, or do I want all together? Now I forgot what basic English means. Let's just go all together like this, all together. I feel like there's a pause in there. All together. F is well-defined, one-to-one, and onto. So F is a bijective function from domain 0, 1 to codomain 5, 100. Hence, 0, 1 and 5, 100 have the same cardinality as, or are the same cardinality. Meaning in a certain sense, they have the same size. So in a certain sense, our sets here, 0, 1, and 5, 100 have the exact same cardinality, even the exact same size, because of the conformance bijection. Okay. Now, last example we are going to do today is this very fun example. We kind of mentioned this before. Let's go up here. Oh, Dutch angle. We don't want that. Okay. Good. Yeah. So we want to prove. It's not straight. Close enough. Okay. So, example, we want to prove that N and Z the same cardinality. We'll prove that N and Z have the exact same cardinality, which is big because that's saying they have the same size. And that's weird because remember, Z is the full number line, positive and negative, whereas N is just the positives greater than 1. I mean, I'm sorry. Z's not the full number line, but it's all the integers at least. It doesn't include the fractions or anything. So all the integers greater than 1, or sorry, Z is all the integers. Whereas n is just all the integers greater than or equal to 1. So it seems like there's a heck of a lot more integers in Z than there are in n. But it turns out not really. They really have the same size because we can form a bijection between them. If you can form a bijection between any two sets, that means you can pair up the elements of the sets. And if you can pair up all the elements of two sets, it's really hard to say that they're not the same size. And we've kind of talked about this before, right? I mean, what do I have around me? Oh, I have coins. Check it out. I have 1, 2, that's a dirty coin. I have, oh, what is this? That's so fantastic. I have 1, 2, 3, 4, 5 coins right here. And I have some number of tacks. Let's not count them. Don't let me count them. Do not count the tacks. So I have some number of coins. I have 5 coins, or I have some number of coins and some number of tacks. So don't even count anything. But notice I can pair up the tacks with the coins like this. So every tack is a corresponding coin, and every coin is a corresponding tack. Right? I can pair them up like this. And notice, maybe we don't know how many coins there are. Maybe we don't know how many tacks there are. But we know there's the same amount of them. Right? There's no tack left over. If there was more tacks than coins, there should be a tack left over. There's more coins than tacks, there should be a coin left over. But we don't have that. Every single coin, every single tack is paired up, meaning they have the same size. So same thing, and that's what a bijection is. It's a pairing up of things, right? Because a bijection is a function which relates an element in A, an element in B, right? That's the pair. But they're all paired up. We know they're all paired up because it's well defined and it's onto, and it's 1-to-1. Onto means there's none left over. 1-to-1 means we don't have like 2 elements of A that relate to an element of B or something like that. It's all paired up nicely. Okie dokie. That's the talking part. Let's actually get to the math and let's get to the doing. So, there we go. So, let's think about what function we could use. So we want to find a bijection from n to z or from z to n. That's what we want to find. So bijection is a bijective function, right? So let's think about what we could use here. So if we want to go from n, which is 0, no, it's not even 0, 1, 2, 3, 4, 5. We want to go from here to z, which is like, let's just say -3, -2, -1, 0, 1, 2, 3. And these both go on. Z goes on in both directions. How could we pair these up with the bijection? That's kind of a natural thing to do. And we wanted to go from here to here. Well, here's the thing we don't want to do. We definitely don't want to go, let's go 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, because we'll never even touch this crap up here. We'll never even touch the negative numbers. So we can't just go in one direction. And there's no way we can start at like the smallest integer, because there's no smallest integer. So we have to go back and forth in sequence. It's the only way that we can hit all the positive, all the negative. So we keep going up and also keep going negative. And I think we should probably alternate going positive and negative. You'll see what I'm saying. I'm saying I think we should send 1 to 0, 2 to 1, 3 to -1, 4 to 2, 5 to -2, 6 is going to go to 3, 7 to -3, on and on and on like that. 8 to 4, 9 to -4, 10 to 5, 11 to -5, on and on and on and on and on and on and on like that, right? And that should eventually go down the line and hit every integer, positive integer, and go down the line and hit every negative. And note this is a bijection. This is well defined. right? There's only one arrow leaving every number here. Every input has a unique output. Or sorry, every input has exactly one output. And notice that none of these go to the same. So it's 1 to 1. It's on 2. We get everything. That's all we need. So we want a function f such that want f of, well, we want f of 1 to be 0. But then we want f of 2 to equal 1. We want f of 4 to equal 2. F of 6 to equal 3. F of 7, nope, f of 8 to equal 4. And then, see, I'm just doing the ones that will get us the positives. And the ones that get us negatives, we have f of 3 will get us -1. F of 5 will get us -2. F of 7 will get us -3. F of 9 will get us -4. On and on like that. Notice what we have here. It looks like the evens are producing all the positives, and the odds are producing all the negatives. So really, we want a function, x, such that, so we want the evens, so we want if n, let's do n here, like energy n. If n is greater than or equal, if n is even, so 2, 4, 6, 8, those guys, we want to create the positive. So if n is 2, we want 1. If n is 4, we want 2. If it's 6, we want 3, 8, 4. Well, how can we go from 2 to 1, 4 to 2, 6 to 3, 8 to 4? Just divide by 2. Notice that if we define f on the even numbers, we do n divided by 2. Well, that will correctly get us all this. We'll get exactly what we want here. Because we're trying to create this function. We don't know it exists yet, we're trying to create it. And it's a similar thing here. If n is odd, right, we want to create -1, -2, -3, -4. Well, how do we do that? We want whatever we have here, we want to make it so that 3 goes -1, 5 goes -2, 7 goes -3, 9 goes -4, etc. So it looks like here, 3 goes -1. It looks like we want to do, well, no, 3 minus 1 divided by 2 will be negative. Or sorry, it will be 1. 5 minus 1 divided by 2 will be 4 divided by 2, which will be 2. 7 minus 1 divided by 2 will get us 3. So it looks like n minus 1 divided by 2 will almost get us what we want. But then we want to take the negative version of that. Only because this will get us 1, 2, 3, 4. We actually want -1, -2, -3, -4. And now the last thing to fill in, I guess, is f of 1 equals 0. But that might actually work already. So right now the function as we have it, let's see what happens when you plug in f of 1. F of 1 is going to be, or it's 1's odd, so in this case we get -1 minus 1 over 2, which is -0 over 2, which is 0. Awesome, so it already works. We don't need a special case for that. It just happens to work as is. So I like this function a lot. So here is our function. This does exactly what we want it to do. This, if you actually go through and calculate it, it sends 1 to 0. It sends 2, or in this case, to 1. It sends 3, or in this case, to -1. It sends 4 to 2. It sends 5 to -2. It sends 6 to 3. It sends 7 to -3. And it keeps on alternating like that, so it should hit every single one. Let's prove it. Oh, crap. Can we remember that we just wrote? I think we're good. Let's say, so let f, and the whole point is it goes from the natural numbers to z, such that f of n equals n over 2 if n even, and it equals -n minus 1 over 2 if n is odd. Make sense? I hope so. So first you have to prove it's well defined. So I'll say need to show that F is well-defined, one-to-one, and onto. So first, well-defined, as I said. We want to do this because it shows F is a bijection, which is important because that shows that N and Z have the same cardinality. I the prize. Always. My prize is the good thing I get inside from teaching people math. So keep my eye on it. So well-defined, 100% well-defined, we need to show that every input has exactly one output. And so the thing to notice here is that notice every, for each, notice that for each input in the domain is in exactly one, or satisfies exactly one case. One case of even or odd. And in each case, the functions n/2 and negative n-1/2 each give one output. Thus, thus each input in N gives exactly one output. Now we did another optional example like this, and really what it comes down to is we're trying to prove that F, no matter what you plug in, only have one output. And notice that any number is either going to be even or odd, it can't be both. So we're going to be in exactly one of these cases. And if we're in the even case, n/2, well, n/2 for any input n is just going to give us one output, right? n/2 doesn't have two results, it has one result, whatever n divided by 2 is. And same thing with negative n-1/2, that has exactly one output as well. You're not going to get two outputs from subtracting 1 divided by 2. It's all one output. It's all well defined. So therefore, n gives exactly one output. So F is well defined. All right, so we're part of the way there. We've proven that F is well defined. Now I'll try to show it's one-to-one. And kind of the reason we thought it was one-to-one before is we were noticing that nothing was hitting twice. That no two elements of the domain were going to the same element of the codomain, because the even numbers were all going to 1, 2, 3, 4, 5, up and up like that. The odds were going to -1, -2, -3, -4, -5, or sorry, -1, -2, -3, -4, -5. And so there was no overlap there. There was no two elements going to the same output. So let's try to prove it though. We prove it in our always standard way. One-to-one, let's do our proof. It always goes like this. Assume there exist A and B in the domain, which is N. Domain. I keep thinking low main. I'm hungry. The domain such that F of A equals F of B. All right. Now we have a couple of cases to consider here. Because depending on what A and B, like we can't just say, oh, this means that A/2 equals B/2. That would be true if A and B are both even. What if B is odd? Then F of B is not B/2, but it's negative B-1/2. It's a whole thing. So we have to really get into it. So note either A even and B even, either A and B even, A even and B odd, A odd and B even, or A odd and B odd. All right, let's do case one. A even and B's even. Then, since A and B even, f of A equals f of B implies that A over 2 equals B over 2 by definition of f. Thus, A over 2 equals B over 2 implies that A equals B by multiplying both sides by 2. That's like case 2. Case 2, we have A, so it works in case 1. In case 1, if A is even and B is even, until you get that A equals B. Case 2 is A is even and B is odd. Hope makes sense, by the way. Like, these are the things we care about, because depending on A is even and B is even, A is odd, B is odd, we get, depending on what the parities are, we get different things when we evaluate the function. So we have to consider every single possibility, every single combination of A and B being even and odd. So A and even and B is odd. Then we have what did I say? Yeah. Then f of A equals A over 2, and f of B equals negative B minus 1 over 2, which of course equals, actually just gonna be like that. Yeah, f of B equals negative B minus 1 over 2. Note, since A is in N, A over 2 is greater than or equal, or yeah, it's greater than or equal to 0. Because the natural number is greater than or equal to 0 divided by 2 is still greater than or equal to 0. In fact, it's actually greater than 0. Yeah. Further, since further, since B is in Z, or since B is in N, B is greater than or equal to 1. So B minus 1 is greater than or equal to 0, which implies that B minus 1 over 2 is greater than or equal to 0 over 2, which equals 0. So B minus 1 is greater than or equal to 0. We're doing some algebra here. So since B is greater than, so B's in N, that means B is greater than or equal to 1. So B minus 1 is greater than or equal to 0 by subtracting 1 from both sides. So B minus 1 over 2 is greater than or equal to 0 over 2, which implies that if B minus 1 over 2 is greater than or equal to 0, that means negative B minus 1 over 2, to flip the sign, will be less than or equal to 0. But hold on. Since A over 2 is greater than 0, and negative B minus 1 over 2 is less than 0, so this means that thus f of A is greater than or equal to 0, and f of B is less than or equal to 0. So f of A cannot equal f of B. It just can't happen. Yeah, because f of B will always be negative, because when you plug in the odd, you always get negatives, plug in the evens, you get positive. That's how f was defined or designed. And so yeah, so we can't have A even and B odd and have f equals f and B. This case makes no sense. Therefore, this case cannot happen. And so if this case can't happen, well, we just don't have to worry about it. So A and B even can't happen. Case 3, A odd, B even, also can't happen for exact same reason. It will literally be the same logic if you just replace A and B. Do not write this on your final or anything like that. Actually do the logic. I'm trying to save you and me some time here. It'll be literally the exact same logic I wrote down. Like I said, just placing A's and B's. So just know it's the same logic. So you can do it just by following the same idea. Now let's look at case 4. Case 4 is A odd and B odd. Then, by definition of F, since F of A equals F of B, that implies since A and B are odd, we're in this case, right? Oh, you can see it. We're in this case right here. So that means that we use negative A minus 1 over B, or sorry, over 2 must equal negative B minus 1 over 2. And then this is going to equal just A minus 1 over 2 is B minus 1 over 2. It's equivalent to that by multiplying both sides by -1. And then A minus 1 over 2, we use some algebra. This is A minus 1 equals B minus 1 by multiplying 2 by both sides. This is going to be A equals B by adding 1 to both sides. The point being, that in either case, so if you have FA equal F of B, no matter what case we show, they'll actually work here. Like case 2 and case 3 will have that. Oh, this case can't even happen. F of A won't equal F of B. The two cases that work, case 1 and case 4, we have that if F of A equals F of B, then A does truly equal B. If F of A equals F of B, then A equals B. So F is 1-to-1 by definition. Here we go. F's got to be 1-to-1. It's got to be 1-to-1 because if you have any two elements that match the same output, those two elements had to be the same. So it can't be different. There's no two different elements that map to the same thing. I did the same thing 1,000 times. So this is why F is 1-to-1. All right. We have one last thing to show. And that is, it would be very nice to show, so show 1-to-1. Lastly, for that F is a bijection, we need to show that it's onto. And it kind of says it's going to be onto because remember we plug the evens in, we're going to recreate all the positives, plug the odds, and we're going to recreate all the negatives. So no matter what, we'll be fine. We're going to prove that. So the proof goes like this. So as always, we want to show that for all M in the codomain Z, there exists an N in the domain, the natural numbers, such that F of N equals N. So for that purpose, let's, along those lines, let M be any arbitrary / particular element of Z. Now note, if it's less than or equal to 0, we're going to have the odds do it. If it's greater than 0, we're going to have the evens do it. So note m is either greater than or equal to 0. Sorry, it's either less than or equal to 0 or m is greater than 0. Case 1, m is less than or equal to 0. So if it's less than or equal to 0, we know the odds will handle it. And which odds specifically? Want n such that negative m minus 1 over 2 is going to equal m. That implies that m minus 1 over 2 equals negative m, which implies that m minus 1 equals negative 2m, which implies that n equals negative 2m plus 1. And notice, if m is negative, then negative 2 times m will be positive. Therefore, negative 2 times n plus 1 will be positive. And so n will truly be a natural number, and it's odd because it's 2 times something plus 1. Which I guess I'll write this as this. This is 2 times negative m plus 1. And notice, since m is less than or equal to 0, negative m, so minus a negative, like if m was 5, for example, or negative 5, for example, negative m will be negative 5, which is positive 5. This is going to be some positive number. It's going to be like the absolute value version of m plus 1. I'm just going to write it like that because I think it makes more sense to me. So that's where we want m to be, 2 times the absolute value version of m plus 1. Let n be 2 times the absolute value of m plus 1. Notice, since m is greater than or equal to 0, 2 times m is greater than or equal to 0, which implies that 2 times m plus 1 greater than or equal to 0 plus 1, which equals 1. This is by multiplying both sides by 2, with 0 times 2, which is 0. This is by adding 1 to both sides. Hence, because n is greater than or equal to 1 and is an integer, and I'll say because 2's in z, m's in z, 1's in z, and z closed under multiplication / addition. So because n is an integer, so n is greater than 1, n is an integer, n is the natural numbers. Because natural numbers are integers greater than 1. And we need that, because that implies thus n is in the domain of f. Now we have to prove that does what we want. We have to prove that we can actually plug it in and get m. The whole point of this is to show that we picked an m. Now let's see if we can find an n we can plug into f to get m. So further, f of n would equal, oh shit, wait. Yeah, so n is an n. So then I'll say note, just because it matters with how we plug things in, if we're going to use the top or the bottom one, note n, which equals 2m plus 1, is odd by our definition we talked about months ago, in fact. Hence, f of n, we're going to use the bottom case, is going to equal negative n minus 1 over 2. Is going to equal negative 2m plus 1 minus 1 over 2 by substitution. Is going to equal negative 2m over 2 by the 1 minus 1 canceling out by simplification, which will equal negative. The 2's cancel out, just leaving us the m's. That's the values of the m's, again by simplification. Make things simple, babe. No reason not to. Simplification. And notice that negative m, since m sort of a negative number, negative the absolute value of m is going to be just m. Since m is negative, m equals negative absolute value of m. All right, and that's case 1. The case 1 tells us that in the case where m is less than or equal to 0, we can sure as hell find, we can sure as hell find an n in the natural numbers so you can plug into f and get m. Now to show if we can also do it for m greater than 0. So normally when in the race, I just ran out of space. Case 2. Is we show for m less than or equal to 0, now we show for m greater than 0. M greater than 0. Now for the m greater than 0, remember it's the evens that we said we plug in to get the positives. And so we want an even such that we're plugging even, you get n over 2. So we want an even so that n over 2 is going to equal m, which implies n just equals 2m, which is good because 2m is in fact even, so this all works out. M greater than 0. Since m is in z, actually no, yeah. M is greater than 0. Yeah, let's do that. Since m is in z, m must be greater than or equal to 1. Since 1 is the smallest integer, bigger than 0. Yes. Then let n equals 2m. Note, since 2 is in z and m is in z, 2m is in z by closure of z under addition or under multiplication. I messed up every word there. Under multiplication. By closure of z under multiplication. Further, because a is greater than or equal to 1, and which equals 2 must be greater than or equal to 2. Hence, n is in z, and n is greater than or equal to 2, which is greater than or equal to 1. So n must be a natural number. So anyway, if n equals 2m, we're definitely going to have n be a natural number, i.e. n is in the domain. So n is definitely in the domain. The question is, does it give us what we want? What we want, again, is a number you can plug into f and recreate this m. So that would show that every m can be hit. At least every m in this case can be hit. We already proved the other case. So note that f of n will equal, I'll say since n even. Oh, actually, we should note that. Note since n equals 2m and even by definition. Then, since n is even, we'll use this top case here. F of n equals n over 2 by definition of f. And then n over 2 is going to be 2m over 2 because we said m equals 2n. By substitution, it's going to cancel, so we get m by simplification. So n is now in the domain. You can plug into f to get m. Therefore, we do this for case 1 too. In either case, there exists an n in the domain n such that f of n equals m. Hence, you guys can see that. So in either case, there's just an n in the natural numbers of domains, so the f of n equals m. Hence, f is on 2. Whew. So f is on 2. Let that marinate. But remember, you remember from like 1,000 years ago, we proved that f was already one-to-one and well-defined. Thus, f is well-defined, one-to-one, and an onto function, meaning f is a bijection. And if f is a bijection from n to z, therefore, by definition, n and z have the same cardinality. Because again, having a bijection between A and B is the exact definition of what it means for A and B have the same cardinality, they're the same size. So even though n is in a certain sense, it feels like only half the integers, they're still the same size set, which is fascinating. They're the same size because you can pair them up and none are left over. So how could they be different sizes? They're just kind of ordered differently in a weird way to think about it. But anyway, that is all I have. I hope these examples have helped. They've taken me a while, but I do it because I love it. I love you guys. So, yeah, email me if you have any questions, and I'll see you guys later.